we have found in this solution with some energy like this, that there's a decaying exponential over this side. And the question is often asked, well, what happens if you try to measure the particle in the forbidden region? Must be a problem. If you find the particle in the forbidden region, it has energy E that is less than V naught, so you have found a particle with negative kinetic energy. How does it look? How can it happen? What's going on? Can you really find the particle in the forbidden region? And then how does this negative kinetic energy look like? And the answer is that it's kind of funny what happens here. You can make two statements. It would be contradictory if you could say the following things. One, that the particle is in the forbidden region. And two, that the particle has energy less than V naught, because then it would mean negative kinetic energy. So if you can say these two things, it seems contradictory. So quantum mechanics evades this problem. Now, this is not discussed as far as I can see, except in some lecture notes of Gordon Baim. And because the argument is not 100% precise, but I think the spirit of the argument is clear, so I want to share it with you. So here is the catch. This particle, remember, it's governed by e to the minus kappa x in the forbidden region. So the length scale here, where you can find it, the particle, the length scale is this forbidden region stretches to about x of the order 1 over kappa. You know, if you are going to find it is in the region of a distance 1 over kappa. At 10 1 over kappa, you're not going to find it. The exponential is too small. But remember what was kappa. Kappa squared was 2m v naught minus e over h squared. That's what it was. Now, if you want to see and declare that you have this particle, you would have to be able to measure position with some precision, with a precision small, a little smaller than this. Otherwise, if you measure with precision 10 times that, well, maybe it's to the left, maybe it's somewhere else. So you need to measure position with delta x a little smaller than 1 over kappa. Otherwise, you cannot really tell it's inside the forbidden region. But now the problem is that if you do a position measurement, and you localize the wave function, there's a momentum uncertainty. The particle that you're looking at, as opposed to the particle to the left, has no momentum. It's a different kind of wave function. There's no momentum really associated or well-defined momentum to it. So because you make a position, you localize in x, whatever wave function you have, you're going to have some uncertainty, and some momentum that is going to be of kind of bigger than h bar over delta x. So a momentum that is bigger than, or a little bigger than h bar kappa. You know, if delta x is less than that, the inequality goes in the same direction. So there's going to be an uncertainty p. And therefore, this particle has now some kinetic energy due to this uncertain momentum. So uncertainty in the kinetic energy is how much? Is p squared over 2m, where p is this uncertain momentum. So this is equal to h bar kappa squared over 2m, which is equal to v naught minus e. So actually, if you think about it, here is v naught. This difference is v naught minus e. And you were going to say, oh, I found the particle, it has negative kinetic energy. But no, the uncertainty principle says, you found it localized? Okay, your kinetic energy, I'm sorry, now has an uncertainty. How much? V naught minus e. So whatever you wanted to prove, it has been disproved. You can't do it. The total energy is now E plus the uncertainty in the energy, which is E plus V naught minus E, and it's therefore greater than or equal to V naught. And no real contradiction. So the uncertainty principle sort of conspires to prevent you from finding a particle with negative kinetic energy. And if you do detect a particle in the forbidden region, it will have energy, total energy 0, or total kinetic energy 0. It will be a normal particle, nothing strange about it.